2, we're finding a volume by taking the region formed by these two curves and rotating that region around the x-axis. So let's draw the graph of this. So we've got y equal minus x squared plus 4. Well, minus x squared is an upside down parabola, and then I shifted up 4 units. So it's something like that. And then y equal 2 is just this line, y equal 2. So the region trapped by those two is that region, and that's going around the x-axis. And so we draw a strip across this thing, and it looks easiest to draw one perpendicular just based on what I've got here. So I'm going to draw a strip perpendicular, and the part that's in my region, I'm going to make it a solid. So I know that what I'm using, because it's perpendicular, I know I'm using the disc or washer method, and it's going to require two discs. That's why I'm calling it the washer method. So it's integral pi, and so I've got radius squared minus radius squared. That's because part of it's shaded and part of it's not shaded, and then this is all being measured from the x-axis, so it's dx. And so the bigger radius goes from that line y equal x all the way out to that curve, which is minus x squared plus 4, so that goes first. And then the second radius, the part that's not shaded, is the part that's underneath this constant y equal 2. And so all I need now is the limits, and I'll get that by setting these two functions equal to each other. And so that gives me x squared equal 2, or x equal plus or minus the square root of 2. And that'll give me the volume if I were to work that out, but I was only asked to set it up. Number 3, again, we're going to set up integral needed. Find the volume of solid. This time the region is formed by these three curves, y equal x, y equal 2x, and x equal 1. So let's draw that. So I've got y equal x. I'm supposed to be red. Y equal x. Y equal 2x is just steeper. And then they both run into y equal 1 out here somewhere. So it's a triangular region. This triangular region here. And I'm sending it around x equal 1. So looking at that, it looks like, to me, the easiest is going to, again, put a strip this way. You could do a strip horizontal, but then right here you're going to have to switch and do a second integral. So it would take 2 integrals to set that one up. This one, but just go down to the x-axis, shade the part that's in my region. This is parallel to the line I'm going around. So I know what I'm using this time is a shell method. So my volume is going to equal integral 2 pi, and then I'll have to do radius. And because part of this is in this region, part's not, this is where I do the subtraction of heights of those shells. So there'll be a subtraction going on here. And this is dx. Okay, so let's start with these heights because that's the easier part. Well, the bigger height, so making this shell that's going around like that. Oops, way around. Making these shells that are going around. So I'm subtracting the bigger one that goes all the way from the x-axis up to the top. That's given by 2x. And then I'm subtracting off this lower shell, and that's given by x. And then the radius. Well, in my picture, this is the radius right here, from the center of that shell out to where I'm marking, where my heights are. And so if this is happening at some arbitrary x, and this line is 1, well then this is x to there, so this would be 1 minus x for the rest of that. So this would be 1 minus x. And then the interval, I'm going to be adding these shells up. It's very clear that those two intersect there, y equal 2x and y equal x. You can set them equal to each other if you want. And then I do this all the way until I hit this other edge, which is at x equal 1, since that's the line I'm going around. And that's forming my border. X equal 1 is my other border. Anyway, so that's the integral using the shell method that will give you the volume of that solid.